In this demo, we'll see how we can build a model to perform link prediction on the Citeseer dataset. We will perform link prediction using graph autoencoders, where we'll use the encoder portion of the autoencoder model to generate embeddings representations of nodes, and we'll use the decoder of the autoencoder to generate link predictions. It'll output an adjacency matrix with a predicted value for whether there exists a link connecting two nodes in the network. Here we are on a new Collab notebook, and I'm running on the T4 GPU link prediction on Citeseer data. Let's go ahead and install Torch Geometric because that's not available by default on Collab. Next, we'll set up the imports for all of the libraries and classes that we need. I'll explain these libraries and classes when we actually use them in our code. The first step is to make sure that we have the right device that we want to use. We have a Cora device enabled. That's what we use to train the model. Next, we download and get access to the dataset that we'll use for link prediction. The Citeseer dataset is a dataset of 3,312 scientific publications classified into one of 6 categories, forming a citation network. This is a very common dataset for node classification and link prediction. We instantiate the planetoid class, which is where this dataset is available, and you can see the dataset is downloaded and ready for use. Now this dataset has a single graph, and down here at the bottom, we have the details of that graph. The X variable, the node features, is a matrix that is 3,327 by 3,703. 3,703 is the binary feature vector, which indicates the presence or absence of specific words from a predefined dictionary. So you can see that this is similar to the Cora dataset that we worked with earlier in this course. Every node has a feature vector indicating the presence of absence of words, and this feature defines that scientific publication is used to describe the scientific publication represented by the node. You can see the edge index there. There are a total of 9,104 edges. In order to perform link prediction, we need to split our dataset into training, validation, and test data. And this can be done for links using the random link split function. This random link split will split the links or the edges of the graph. Let's take a look at the transform that will apply to this graph data that we'll read in the Citeseer dataset. T-normalized features is used to row normalize the attributes of each node so that the attributes sum up to 1. T-dot to device will move the entire graph structure along with the features and labels to the device, which we'll use for training. That is our GPU, and random link split will split our graph into training links, test links, and validation links. Num_val is the percentage of data that we'll use for validation. So 10% of the links will be validation data. Num_test equal to 0.2, that is 20% of the links will make up our test data. When you use a data set for link prediction, you need to have both negative and positive edges. Positive edges are the existing edges in the graph that actually represent connections between nodes. Negative edges are non-existing edges that are randomly sampled from the set of node pairs that do not have an edge between them. This negative sampling ratio of 1 specified for random link split determines the proportion of negative edges to positive edges in the generated dataset. With the ratio of 1, it means that for every positive edge that actually exists in your graph, there will be 1 negative edge in the dataset. The negative sampling ratio thus controls the balance between positive and negative examples in the generated dataset, ensuring that the model learns to predict both existing and non-existing edges correctly. Then random links split generates training, validation, and test datasets. It ensures that each dataset maintains the specified negative sampling ratio. However, we specified this additional parameter, add negative train samples equal to false. Only for the training data, no negative samples will be generated. That's because during the training process of this model, we'll generate negative samples for each epoch of training separately. Now, the citation graph that we are working with is an undirected graph, and that's why I've set is undirected to true here. On line 13, I instantiate the Citeseer dataset and pass in this transformation that we've specified, and we access the train, validation, and test data and print out their details to screen so we can see what these different datasets look like. And here are the results. Now, at first glance, these results are very confusing, especially the edge index values. Why does the validation data have 6,374 edges? Why does the training data have 6,374 edges, and so on? And if you scroll over to the right, what are these values for edge labels and the edge label index? We will discuss these in the next video.